In this video, we will discuss conservation of momentum and elastic collisions. We will define what an elastic collision is and explain how conservation laws, notice there's plural here, laws, are applied to elastic collisions. Now, the conservation laws concerned are conservation of momentum and conservation of kinetic energy. Finally, we will solve some problems to highlight the concepts explained. The definition of elastic collisions are as follows. Elastic collisions are collisions for which the momentum is conserved. That is, the momentum of the system before the collision is the same as the momentum of the system after the collision. So, conservation of momentum applies. Another quantity that is conserved in elastic collisions is kinetic energy. So kinetic energy before the collision is the same as the kinetic energy after the collision of the system, representing no loss in kinetic energy during collision. So for elastic collisions, conservation of kinetic energy applies as well. So let's apply conservation of momentum and conservation of kinetic energy to a typical elastic collision. So in the diagram shown, you have two masses, mass 1 and mass 2, that are initially moving towards each other. Mass 1 has a velocity of v1i, so the subscript I refers to the initial state. Likewise, mass 2 is moving to the left with an initial velocity of v2i. So they collide elastically, and after the collision, represented by this final state, m1 has a velocity of v1f, and m2 has a velocity of v2f. Now let's not worry about the direction of motion after the collision. Just it's enough to identify the two velocities. Note, we are using the subscript f to denote the final state, namely state after the collision. The conservation of momentum says the momentum of the system before the collision, that is m1 v1i plus m2 v2i, is the same as the momentum of the system after the collision, which is m1 v1f plus m2 v2f. So this equation represents conservation of momentum applied to the system before and after the collision. Now, since this collision is elastic, the kinetic energy is also conserved. So the kinetic energy before is the kinetic energy of mass 1 before the collision. So that is 1I squared, half mv squared. Essentially, that is the equation of kinetic energy. The kinetic energy before the collision for mass 2 is half m2 v2i squared. After the collision, the total kinetic energy is conserved. So half m1 v1f squared plus half m2 v2f squared. So this line represents conservation of kinetic energy applied to the system before and after the collision. Let's rearrange the terms in these two equations for later use. Now for conservation of momentum, we can move that term to this side and this term to that side and rewrite it as follows. So doing that will give you this equation derived from there. We can also manipulate the kinetic energy equation in the same way. Note all the terms have half, so that half goes away. Now I can move this term to the left and that term to the right, resulting in the following line. Now I can factorize the left-hand side and right-hand side according to the following, which will give us a neater version of the equation. Now note, if I take the kinetic energy equation divided by the momentum equation, we will immediately see certain terms will just go away, such as m1. The difference in the velocities of object 1 before and after collision will also go away. On the right hand side, m2 will go away, and likewise the difference in the velocities of object 2 before and after the collision will also go away, and that will leave us with this equation which has no mass inside. Now let's rearrange it a little bit further to get the following. So I'm going to move this to this side and that to that side. So I'm going to get v2f minus v1f. Now this is a relative velocity equation which says the velocity of object 1 relative to object 2 prior to collision equals to velocity of object 2 relative to object 1 after the collision. The good thing about this equation is that it is mass independent. It does not have any mass in it, so it's easier to deal with. So let's emphasize an important point. This equation is the result of manipulating conservation of momentum and conservation of kinetic energy. So conservation of kinetic energy is an important ingredient in getting this equation. So this equation in the box, the relative velocity equation, is true only if the kinetic energy of the system is conserved in a collision. Namely, it's only true for elastic collisions. Just to highlight the concepts we covered, let's look at problem 1. So you have a couple of masses, mass A and B. Mass A is 0.5 kilograms, mass B is 0.3 kilograms, are moving towards each other with a speed of 2 meters per second as shown in the diagram. Suppose the collision is elastic. Now find the velocities of these masses after the collision. So let's say after the collision, A moves with a velocity of VA final and B moves with a velocity of VB final. So that's what we want to determine. So let's use the conservation of momentum to first obtain an equation. So the momentum before is 0.5, that's the mass of object A, times 2I hat, so because object A is initially moving to the right, plus the momentum of object B prior to collision is 0.3 times minus 2I hat. Now after the collision, object A moves with in some ways which we don't know yet, that's what we want to determine. And object B, the momentum is 0.3 times VBF. So we want to get VAF and VBF, two variables, so we need one more equation. The second equation that we can use is the relative velocity equation that we derived a few minutes ago. That says the velocity of object A, which is 2I hat, relative to velocity of object B minus 2I hat prior to collision equals the velocity of object B relative to velocity of object A after the collision. Note the left-hand side from this equation, the conservation of momentum equation, is quite simply 0.4I hat. And the left-hand side of the relative velocity equation is simply 4I hat, which we can write here, 4I hat. So we see that we have two equations and two unknowns that we can solve simultaneously. It's just an algebraic equation that we can solve simultaneously, and if we do, we will get the following for VAF and VBF. So the velocity of A after the collision is minus I hat meter per second, which means it will be moving to the left with a speed of 1 meter per second. The velocity of B after the collision is 3I hat meter per second. That means it will be moving to the right with a speed of 3 meters per second. That solves the problem. Now let's look at problem 2. An object with mass 0.35 kg, that's this one, is moving on a frictionless air track. Its initial speed is 1.1 meter per second. To the right, as shown in this diagram. It undergoes an elastic collision with an initially stationary object of unknown mass. So that is this mass that is not moving. The mass is m, which we want to determine later. After the collision, the first cart continues in its original direction at 0.62 meter per second. So that is the blue mass. Find the mass of the second object and also the speed of the second object after the collision, that is v. So first, let's write down conservation of momentum equations for the system. So the momentum before of the system is mass is 0.35, that is this mass right there. The velocity is 1.1 I hat. The second mass is not moving, so there is no momentum there. The final momentum of the system is again 0.35, that's the mass of the blue object, and it's moving with a velocity 0.62 I hat. The red box, the mass is m, we don't know, and the velocity is v. That will give us the product mv to be 0.168 I hat, or quite simply, if we drop the vector sign, 0.168. So let's box this equation. Now there are two unknowns, so we need one more equation. Now let's use the relative velocity equation again. So what that equation says, relative velocity equation, that says the velocity of the blue object relative to the velocity of the red object prior to collision, which is 0, equals the velocity of the red object relative to the velocity of the blue object after the collision. So you see, you can immediately get the velocity of that red object as 1.72 I hat meter per second. So now substituting v to be 1.72, the mass of the unknown mass of the red object can be determined as 0.168 over 1.72, and that will give you the unknown mass as 0.0976 kilograms, or in grams 97.6 grams. So that solves the problem. We can also use the kinetic energy conservation equation to solve the problem. So let's go ahead and do that. The kinetic energy before the collision is half times 0.35 times 1.1 squared. So that's the kinetic energy of this object. The kinetic energy of the second object is 0, equals the kinetic energy after the collision is half 0.35. The speed is 0.62 squared. Kinetic energy of the second object with unknown mass is half mv squared. Of course, we can solve for mv squared from that equation, and that will give us mv squared as 0.289. So we have two equations, 1 and 2 now, that we can solve for m and v. So dividing mv squared by mv, we get v, and that's going to be 0.289 over 0.168, which will give us 1.72 meter per second as before. And having found the v, you can substitute the v inside here to get the m to be 0.0976 kg as before. Thank you for watching, and have a great day.